Thank you very much. I hope you can hear me.
Yes.
So I will talk about ferroelectric materials and their surfaces and interfaces and their behavior at the nanoscale. This is work that I mostly did at ETH as a Marie Curie Fellow, and I'm carrying on now at LSPU. So I'll start by asking what is a ferroelectric material. We might all know what it is, but just to start all on the same footing, and then talk about what are the issues at the surfaces and interfaces using a number of examples and looking at some applications of nanoscale ferroelectrics. So I will talk about perovskites. Not all ferroelectrics are perovskites, but this is the type of material that I've been working on. You can have all sorts of structures. So in a non-ferroelectric paraelectric perovskite, you have A site, B site, and B sites at the corner or at the center of a cube, and the oxygen atoms on the faces. When the material is ferroelectric, what happens is that some or all of these atoms go away from their high symmetry positions. So in this example, we have that the atoms on this central plane have moved away from the high symmetry position. The B site atom has moved up, but the oxygen atoms have moved down. Now the A and B sites have a positive formal charge, while the oxygen atom have a negative, -2 generally formal charge. So here because they're not more on the same plane, they form a little dipole. And if we sum all this little dipole over a whole crystal, we get macroscopic polarization. And obviously, as we moved the atoms in this direction, in the same way, we can move them in the opposite direction. So there's two equivalent directions to the polarization. Now, these two equivalent directions become inequivalent when we start looking at a thinner form of matter. So for example, a thin film. Here we have a substrate and then a few unit cell of the ferroelectric material. And if we move the polarization up or down, it is different. So for example, they will give a different signal with piezophore microscopy, for example. And that means that they can be very useful for applications. So these are some of the applications they're useful for. This is quite an old article, but I think it's really nice because it's a non-scientific paper. It's a sort of general interest article written by some of the giants in the field. So I think it's a really nice read if you're interested. I will sort of be focusing more on the applications in memories. So this up and down polarization can be treated, can be looked at as the logic bytes. So ferroelectric memories do exist. So this is an example of one, is a lead zirconium titanate memory. And the way they work at the moment is that they're integrated in whatever is the architecture of the dielectric memories. So instead of having a dielectric, you have a ferroelectric material. There is advantages to that. The advantage being that for a dielectric, you have to run a constant current to keep the polarization going, whereas the polarization in a ferroelectric is intrinsic. So you only need current to switch the polarization up and down when you want to switch your byte from 0 to 1 or vice versa. However, the goal is explaining this rather rubbish drawing here, where we want to sort of dispense of this architecture, have a more compact type of device where we could have a thin film of a ferroelectric with many different domains. So domains are part of the ferroelectric which have different polarization that we can switch, and each domain is a byte. So this is the idea. And obviously, because we want to go towards miniaturization, we want to use just a very little thin film of material, of ferroelectric material, to do that. So how doable is that? Well, that's what we're getting at. So one characteristic of ferroelectric surfaces and interfaces is that they are charged. So this ferroelectric polarization induces what are called bound charges at the surface or at an interface. So here we just have sort of mostly positive charge, on the other side a negative charge, and the other way. And we know from literature that if you have a surface charge, it's the surface energy becomes infinite, so it's unphysical. So the system will try to want to compensate these surface charges. And so how does it do it? So I'm just going to go a little bit through the literature, what we know about how the system tries to compensate the surface charges. So let's say that we have a ferroelectric material, and in blue, this is the interface. It can be vacuum, it can be a metal, an insulator, or whatever. So if we have a ferroelectric polarization, which induces these bound charges at the surfaces, then the surrounding will try to compensate them. So whether it is a metal or by absorbing molecules on it. But generally, this will be imperfect, this screening, especially if we think of a metal, there's a screening length. So there will be a little bit of a remnant charge remaining on both sides. And this remnant charge, so now we have basically a capacitor, and there is a field within this sort of tiny capacitor, which we call the depolarizing field, which does exactly what it says. It kills the polarization. So what was found is that below a certain thickness, there is a critical thickness that below which the polarization is 0, which is really inconvenient for the applications that we want to look at, because we want to have ultra thin ferroelectric film with robust ferroelectric polarization. So people have been looking a little bit at how to deal with this, or how to contrast this. So whether through the interface structure, by sort of by the bonding at the interface, or on the surface structure, whether with defects or adsorbates, or through electronic effects like excitation of electron and holes. So what I'm going to be talking about for the next bit of the talk is trying to sort of tidy up what we know about these systems and how the electronic properties of bulk electronic properties of the system will affect the response to going to the ultra thin limit. So I will look at 3 cases. The first case is ferroelectric materials with neutral layers. An example of this is lead titanate. Lead titanate, so lead has a formal charge of +2 and titanium of +4. So if we look at the 001 direction, so 001 surfaces, these are formed of stacks of lead oxide and titanium oxide. So 2 minus 2 is 0. So these all have 0 charge. These layers are all neutral. And we did a number of density functional theory calculations for this, and so we found a couple of things. So lead titanate has a critical thickness of 7 unit cell, and even at 7 unit cell, the polarization is not that robust. It will be robust at an electrode, but it goes to 0 towards a surface. But it's really enough to add what I could like to call up or down friendly features to impose a robust bulk-like polarization in either direction. So for if we want the polarization to be P up, is enough that on top we put oxygen add atoms, for example. If then we want to reverse it to P down, we can remove the add atom and add a titanium add atom. So just having this compensation, so this charge at the top will be enough to reverse the polarization from up to down. We did this work together with some experimental collaborators who do in situ second harmonic generation. Without having to explain too much about what that is, if the material is ferroelectric, they get a non-zero signal. Otherwise, the signal is 0. So any one of these points, which is non-zero, means that there is ferroelectricity in their system. So they were looking at lead titanate growing on a metal And what they observed is that it grew without critical thickness. So you see that at 1 or 2 unit cell, they already have a signal. And the way that we explained it, the only way they can work is that they must have some, so the polarization was P up. On strontium ruthenate, lead titanate only grows P up. So they had to have some P up friendly features that we then identified to be lead vacancies towards the interface, which stabilize the polarization below. And then they saw that after the growth, there was a drop in the polarization, and then the polarization would resume at the same value as before the pause, as soon as they started growing again. And so it has to be something that occurs at the surface. And the most simple explanation, and that turned out to be true from further experiments, was that these vacancies that are needed to stabilize this polarization at 1, 2 unit cell, they need somewhere to go. And they go on the surface and they stabilize on the surface after they start growing. And they turn the polarization down. So there is this sort of 2 areas we can kind of fight for which direction the polarization needs to go. Now, as I said, this happens in PTO, and when it's grown on strontium ruthenate, and you can grow only with the polarization going up. So what we thought, well, if we have the polarization going downwards, what happens? Is it possible that we can really stabilize a strong polarization downwards just because the system naturally puts this lead add atom on the surface? And that's exactly what it does. So on the lanthanum strontium manganite, which is another metal, they were able to grow the film with a really strong downward pointing polarization following this mechanism. So what we found with this bit of work was that the stability and the direction of the polarization can be really determined by the interfacial defect chemistry. The second type of material that we looked at are ferroelectric materials with charge layers. So in this case, we take bismuth ferrite as an example. So it's a 3-3. So along the 001 direction, it's got the same stacking of A site oxygen, B site oxygen 2, but with a charge of +1 electron and -1 electron. So we can think of these layer charges as a type of polarization, which we call layer polarization, and we can calculate to be plus and minus 50 microcoulomb per centimeter square, which also results in some surface charges. So if we add to this layer polarization a ferroelectric polarization, we can do one of 2 things. Either have the 2 in opposite direction, so the overall surface charge is decreased, or in the same direction and the overall surface charge is increased. And we gave this the technical name of happy and unhappy systems, because if you remove some of the surface charge, you're removing some of this sort of strain on the energy, surface energy, and the system is happier, I suppose. And the funny thing about bismuth ferrite is that these 2 components of the polarization have exactly the same magnitude. So when they are in the opposite direction, the system is really, really happy. The surface charge is 0. So with bismuth ferrite, you have 0 critical thickness, up down to 1 unit cell. It presents a ferroelectric polarization. It is very, very hard to switch, which is not very nice when you want to have it in a memory component and you have to continuously switch it up and down. So to show you this is the happy system. So you see that for 6 unit cell, this is the polarization, and it's perfectly robust at 50 microcoulomb per centimeter squared. When we switch it, and I don't know what's going on by itself. When we switch it, the polarization goes down to about 25, 30, and also the strontium ruthenate, the metal, has to distort. And the difference between these 2 systems is about 2 electron volts. So it's really, really not very nice to switch. The third example are ferroelectric materials with charge layers. So in non-ferroelectric materials, which has polar layers. The example here is potassium tantalate. So potassium tantalate is almost ferroelectric. It's called incipient ferroelectric. So its ferroelectric transition temperature is negative Kelvin. So it's not ferroelectric, but very little can make it ferroelectric, a bit of strain, a bit of doping. And so we use this material as an example because it is easier to distort. And what we found is that, so it has layer charges of the same type of bismuth ferrite. So it's actually it's +1 for the B site and -1 for the A site. So then the polarization, the layer polarization and the induced charge is ±50 microcoulomb per centimeter squared. And if we relax this structure using density functional theory, we find that it distorts. And it distorts in a way that it induces a ferroelectric-like polarization, which compensates the surface charges. So we can make a ferroelectric material out of a paraelectric material if there are these charge layers. So this is how it sort of goes with the thickness. So it is more or less 50 up to 80 unit cell, and then it starts going down. So this is the imposed, the additional polarization which occurs in the system. And we made an electrostatic model to explain this. So after a certain thickness, then you start having excitation of electrons and holes. And they contribute to compensating the surface charges. So there is not need to have such large distortions as for the thinner layers. And as I said, we used potassium tantalate because it's very easy to polarize. We also tried to have a look at the very opposite side of the spectrum, which is lanthanum aluminate, which is another perovskite, which absolutely doesn't want to polarize. It's got a very, very stiff sort of potential energy shape. And even in that case, at very thin level, so 4 or 5 unit cell, it will develop a very small ferroelectric polarization in response to the fact that it has charge layers. Now, we can't really do anything with 3 microcoulomb per centimeter squared of ferroelectric polarization, but this is the very opposite end of the spectrum. So there will be a lot of variance between these two materials. So what we found then is that the electrostatics of the system really influence how the system responds to the ferroelectric polarization, or how the ferroelectric polarization responds to being in the ultra thin level, and whether the system has charge layers or not is really, really important. So now we know how the systems behave. The big question next is understanding how can we make them switch easily. As I said, for bismuth ferrite and also for this third type of materials, really these layers these charge layers lock the polarization direction. So there might be things that workarounds to that, but maybe these are the set of materials that look more promising, but sort of there's more work to be done on this. I want to do one last example, which I think is quite fun. And it's showing ferroelectric materials in a different field, the field of catalysis. And where I think there's they have quite a lot of potential. So, and this is by using dynamic catalysis. So in dynamic catalysis, we want to cycle through 2 or more states of the surface to enhance the catalytic properties. This is an example with temperature for a material which is ferroelectric below a certain temperature and non-ferroelectric above. So one example could be that below the ferroelectric transition temperature, so when the material is ferroelectric, it helps, so the surface charges help triggering chemical reactions. So for example, water dissociates. And then when we go above this temperature, the absorption of these products becomes weak, and they go away, and new water molecule absorb, etc. So there's many of these examples in the literature. So we tried to, together with Ipek, who is a master's student at ETH, we tried to build a dynamic catalysis cycle using bismuth ferrite. So we looked at the absorption of water on the happy bismuth ferrite without surface charges, and the water absorbed molecularly. If we switch the polarization and go to the unhappy system with the charged surfaces, the water dissociates, and not only it dissociates, but the hydrogen will remain strongly absorbed onto the iron oxide surface, which is negative, and the OHs to the BiO surface, which is positive, and the rest will want to dissociate, to desorb. And when we switch the polarization again, there will be further desorption of the products and new water molecules come in. So we have been doing some work with experimental collaborators at ETH who have tried to see if it happens. So they took a cobalt ferrite nanoparticle. So cobalt ferrite is magnetostrictive, which means that it gets strained by magnetic field, and coated with bismuth ferrite and put it under AC magnetic field. And what they saw was that after they had some methanol, which stops recombination because it's a whole scavenger, they saw really quite large hydrogen evolution. So this is all very nice, but does it relate at all to the cycle that we were talking about? So it's definitely not the strain itself, which is sort of favoring dissociation, the dissociation of water. We looked at the strain and the response of the polarization to the strain, and it's basically zero. And we also looked at the water absorption on the bismuth ferrite, and it doesn't change with strain up to 3%, and experimentally they're well below 1%. So we think that it has to be with something like this, with the polarization changing away from this happy state, so that it doesn't have to change to reverse completely, but at least some surface charges have to be revealed, and they become, where the surface charges are, you have the active sites for the catalysis. So we have some ideas, and this is something that we're working on. The flex electric effect could be one. If we have strain gradients, they've been found to be places where the polarization locally reverses. So you could have a happy system which becomes locally unhappy. The polarization could rotate in plane at very high tensile strains, although I'm not sure. I think this is the least likely. Or you could have a domain wall motion. So between two domains, you can have, it's found in the literature that strain can induce the motion of the wall by one or more than one unit cell. So that would create, again, local active sites that could sort of be going back and forth. Probably this is more likely. It's also likely that these might happen at the same time. And that's about it. So I talked about how the electrostatic boundary condition influence the stability and the switchability of nanoscale ferroelectrics. We now understand a bit better how to make them stable, but not so much how to make them switchable. And there's other applications for which we really need to understand these nanoscale ferroelectrics very well. And these are the people I work with. So thanks to all of them, and thank you for your attention.